everybody. I hope you can hear me well. Welcome and happy Tuesday. I don't know about you, but I personally am still recovering from all of the eating that I did on Thanksgiving. But I'd like to welcome you back to another month of our Innovate seminar series. And this month we're welcoming the winner, the champ of the best condensed matter oral presentation during the conference. And I am super excited to hear her speak today because I didn't get to see her at the conference. So super interested about what these crystals are. But with that, I'm going to turn it over to our programs committee chair, Carlton Smith, to introduce our speaker.
Hello, everybody. So thanks for coming to what I believe is the third Innovate seminar for this semester. And I am very, very, very pleased and honored to welcome this month's seminar speaker, LaToya Anderson. So I have had the pleasure of knowing LaToya for going on around about a year and a half now. LaToya is an undergraduate physics student at Brooklyn College. She is also an associate research scientist at the Simons Foundation, working in their Flatiron Institute's Center for Computational Quantum Physics. She is an alumni of the Simons NSBP Scholars Program. And as Elon mentioned, she is also the winner of the 2022 NSBP Conference's Best Oral Presentation in Condensed Matter Award. And I think that being said, I will turn it over to LaToya for what is sure to be an excellent, insightful, and exciting talk.
Thank you, Carlton. Thank you, Elon, for that wonderful introduction. I really appreciate it. And thank you so much for, of course, inviting me to even give a presentation for the Innovate seminar series. So with that, I'm actually going to get started with sharing my screen. So give me 1 second. As Carlton mentioned, I'm giving a talk today on exploring superatomic crystals. And just a little bit about me, a little bit more background and context. I did not actually start off thinking I would be a scientist when I was growing up. I grew up in a very artistic family and eventually studied classical ballet and modern dance for a bit of a decade, on and off, and eventually earned my first Bachelor of Arts degree in dance from New School University. Then, as was mentioned, I transitioned over to STEM, and that mainly was because I wanted to study, I wanted to figure out what is there a way to study something that allows me to learn how does something work, how is something put together, how does something function. And science is a great way to be able to investigate those questions. So as said before, I'm earning my bachelor's degree in physics. I'm also working at the Flatiron Institute where I'm studying superatomic crystals of all things. So let's actually transition over to what that even actually means. So I work within the Berkelbach Lab Group. The Berkelbach Lab Group, which is part of the Flatiron Institute as well as Columbia University, we actually focus on developing computational methods to apply them to quantum chemistry. What does all of that mean? Basically, what are some software ways that we can study atoms, molecules, solids, right? So a solid, for example, if you were to zoom out, that could be anything from a computer to a table to a glass of water. And then if you zoom in, all the way in, now you're looking at an arrangement of atoms that form a pattern to make that solid. So that's what they try to figure out how to do, and there's various methods of how to do that. So the topics that I'm going to go over during this talk are what is a superatomic crystal, right? We have to put a little bit more context into what we're actually studying. Next, I will talk about how we actually use computational material science techniques to discover the properties of these superatomic crystals. And then, what are some potential applications of these crystals for technologies? So first, let's start with the superatomic crystal. Even with a crystal is made up of lots of atoms. So we have to zoom in even more and ask ourselves, what is a superatom? So this actually is a picture of a superatom. And a superatom is a stable, discrete cluster of atoms. Basically, a bunch of atoms that are bonded together. Now, you might think, well, lots of things. There are lots of combinations of atoms that we already have. What makes these special? It's the fact that they can mimic the properties of traditional atoms. Those traditional atoms are what we see on the periodic table. And that periodic table, depending on the placement of those atoms, tells us this atom here is a metal. This atom here is a non-metal. These group of atoms put together can make plastic or they come up with wood, for example, right? But in this case, if we're able to put a whole bunch of atoms together, but they have the same properties of what you would find on the periodic table, that's really special. So this complex structure allows us to tune for magnetic, electrochemical, and photonic properties. What does even any of that mean? It basically means we have a much larger recipe book of atoms that we can put together that mimic the properties of traditional atoms, and we can use them in technology. Currently, we use silicon, among many other trace metals, in order to run our cell phones, right? Now, the problem with silicon, as you'll find out later, is that it's kind of expensive to manufacture, and there are some disadvantages with using silicon. But if we can construct a superatomic crystal that has the same properties of a silicon atom, but has other advantages, there's a potential to replace that type of material. So the size, they're between molecules in both solids, and they have what's called capping ligands. What that just means is there are these extra atoms, so that's the green atoms that you see on this superatom, and they stabilize the cluster. It basically makes sure it doesn't fall apart on us. And that also helps us to direct its assembly, just even making the superatom in the first place, as well as controlling the coupling between clusters. And that just means these ligands help us to assemble all of these superatoms together to form this crystal that we're going to talk about in the next slide. By assembling all of these atoms together, now we're beginning to play with the locations, quote unquote, of the electrons. They start to shift and move around a little bit, and that helps us to then be able to use the properties that could be used for, like I said before, electronics. So that's what we mean when we say the assembly leads to a highly delocalized electronic structure of their S-like, P-like, and D-like orbitals. Some examples include metal chalcogenides, fullerenes, and aluminum clusters, and all of these different types of assemblies of atoms or clusters of atoms have their own unique properties that we're not really going to go into today, but those are just some examples of what's considered to be a superatom, if you are familiar with them. Now, crystals. Now that we know what a superatom is, we put a bunch of them together, we form this crystal. And so what we're seeing here in this picture are two different layers. So you'll notice in the center here that there are these green atoms, those are the chlorides, and there's no apparent bond, but there is actually a bond. It's weakly bonded together. And so that means we actually have two layers. We have a top layer and we have a bottom layer. And this is taking the viewpoint of looking at it from head on, like we're holding this, we're not really, but holding this and we're looking at it head on, and there's multiple layers. The fact that we have this type of a system allows us to manipulate the system. So I said before that there's not a whole lot going on in terms of what's happening between these layers. That's important because that means that an engineer, if once they start constructing, let's say, the larger multiple layers of this, and let's say we need to shave it down, we have the opportunity to do that. And that's because of the fact that we have these weak bonds in between these two layers. So the system we've been looking at this whole time, there are 6 atoms, 8 seleniums, and 2 chlorides for each of these clusters. And so I mentioned before about the fact that we have these 2 layers here, and that's as if we're looking at it straight on. And then if we were to look at just this top layer alone, from the top view down, that's what you're seeing on the right side of your screen, right? It should be the right side of your screen. So this top view shows us now that these atoms are bonded together, but these bonds are what we call covalent bonds. They are super, super strong compared to the bonds between these green or chloride atoms. And that's important as well, because as we're shaving this down from, let's say, a cube of this 16 atom, multiple 16 atom system down to just a single sheet, which is what you see on the right side, this single sheet won't fall apart. And that's really important because that single sheet can help us to then be used in those technologies that we talked about before. So why are we even studying this 16 atom multiple cluster system? We're studying it because it has the properties of a semiconductor. Semiconductors are what's used in electronics, in fuel cells, and quantum computers. And so therefore it has potential applications to improve all of those technologies. Year, further study is needed. We've only just started to study these systems within the last 10 years or so. And so therefore we need more scientists, we need more undergraduate students who may be interested in computational science to take an interest in learning more about these systems. So how do we actually use computational material science techniques to discover these properties? It all starts with math. And don't worry, this will actually be the only equation, the only equation that you're going to see in this entire presentation. But this equation is really important. It's called Schrödinger's equation. And it's used to describe what's called the electronic structure of either an atom, a molecule, or a crystal structure. What does that even mean? So we're looking at here in this bottom photo, a picture of hydrogen. So hydrogen has 1 proton and it has 1 electron. Each of those has its own amount of energy. We can use the Schrödinger equation, solve it exactly, means we can get a precise number that tells us how much energy this hydrogen atom actually has. However, once we get larger than this hydrogen atom, then it becomes nearly impossible, computationally impossible, to solve for single numbers that describe this type of a system. But not just hydrogen, going further than a hydrogen, even helium, you need to start making what we call approximations, which just means now we need to make some assumptions so we can remove some of those terms or simplify some of these terms in order to then say, okay, this structure we're studying has this amount of energy in it. So this is where density functional theory comes in. And so this graphic is actually a great visual of what's actually happening. So I mentioned before about how we can use the Schrödinger equation to understand the amount of energy a hydrogen atom has. But once we go beyond that, like in this system here, we have 3 electrons. And then on the bottom here, we have this 1 ion that is attracting these electrons to it, right? And so what normally happens is that because you can't necessarily assume that electrons are in these specific locations you need a class in quantum mechanics to understand why. But essentially, there's a probability of where these locations are. So you have to understand all the locations of where these electrons can be. But instead of taking that approach, DFT takes a very different approach. It says, if we were to look at here, one spot or one circular or spherical section of this atom, or if we were to look at this entire sphere of this atom, right, with mainly focusing on the electrons, how much energy does this spot here, this spot there, this spot there has? We're looking at the density of these electrons in terms of its energy. That's essentially what DFT is. And so we use DFT to understand the structure of, or the energy of this structure. Not only the energy in terms of just the system itself, these systems vibrate, so we can understand its vibrations. We can get a sense of its electronic structure of the atoms, of the molecules, and even of solids, which is what we're talking about today. And it's considered to be the workhorse for computational material science, meaning it's used incredibly often because it's pretty accurate and it's very, very good at giving us an idea of what's happening on the atomic scale or the quantum mechanical scale. Now, the great thing is if you want to do this type of work, you don't have to do the math because there are software packages that do this math for you. You just have to input these are the atoms that I want to study. They are arranged in this specific way. Plug all that and a little bit of extra information into any of these software packages, and those software packages will then tell you these are the energies that are within your system. And so that's really important because all you really need is an interest in quantum mechanics as well as some programming experience, right? Because you are going to hit some roadblocks along the way with using any of these packages. Because most of these packages are free and you can actually start studying these atoms, molecules, etc. on your own just from your laptop. And that has allowed us to develop a worldwide STEM community that has a growing interest even in software development. And the reason I'm even bringing all of this stuff up is not only because of the fact that this is what is done in computational material science, it is what allowed me to be able to do research even when I couldn't get into a traditional lab. And so one of the issues one of the challenges that many students face is trying to enter into some sort of physics lab to gain research experience. And that was something that I faced, right? Especially during the pandemic. And so I decided to try to see, are there software packages that scientists use? Of course, here we are. And then by developing those software skills that allow me to be where I'm at today, here at the Simons Foundation or the Flatiron Institute. And so the main packages or the package that I used was something called Quantum Espresso to study the superatomic crystal that we're going to talk about. So I talked about the electronic structure. This is really what we're talking about. So all we're seeing right now, especially if you may not be familiar with this, are a whole bunch of lines that are going across our screen. So the way you look at this is this graph has two sections. The bottom section here, where that's closer to all of these letters, those lines are the potential places or the potential energies of our superatomic crystal in terms of the electrons that are super important to us, right? So this bottom section of these band structures, that's what we call them, because they look like bands or whatnot. These help us to learn more about the system itself. Now, you might be wondering, well, what about this top section of all of these, also known as spaghetti lines, right? That tells us in terms of the distance between these two sections, well, if I figure out a way to excite the electron. That excited electron likes to jump, quote unquote. So it jumps from the bottom section of these spaghetti lines to the upper section, and it's going to go to the closest upper section. And so here, what this is telling us is that because the distance between these two sections is not that large, that's a good thing. That means it's actually a semiconductor. That means that we can send a photon, we can send some sort of energy, send another electron to this superatomic crystal. The electron will easily jump from the bottom section of this band, we call these the valence bands, and have it jumps up to what we call the conduction bands, or this upper level here. So I mentioned about that distance. That's called the band gap, and that's really what we're looking for. In addition to that, these lines here, if you were to see the same type of picture or plots, but with silicon, you would see that the lines are just all over the place. They cross each other. They really look like spaghetti. These are fairly flat. And that's what we're talking about in terms of the electrons themselves. That means that we can fairly easily excite an electron, let's say on this top band on the bottom section here, excite it up to the next band up in the conduction band area, and it won't interfere with any of the other electrons. Therefore, we have more control over this superatomic crystal. And so that gap, we call that band gap. This is what confirms to us that we have a semiconductor. So I won't go into too much detail about this, but basically on the left-hand side here, this tells us based on the atoms, which are rhenium, selenium, and chloride, this tells us the contributing energy. How much energy does chloride contribute to this entire system? How much energy does selenium contribute? How much energy does rhenium contribute? And that's what we're looking at here. The higher the peaks, the more amount of energy it potentially gives to us. On the right-hand side, this side is the conduction band side. So when the electron is excited, it goes from the part where all the parts are filled in to the parts where it's not filled in. The higher the amount of energy, which is what we're seeing with the green, which is the rhenium, that means that it's the rhenium, the electrons are going to jump to the energy levels contributed by the rhenium. That's what this is basically telling us. Now we're like, okay, great. So now we know what's happening in terms of the atoms. What if we need to get into the nitty gritty and figure out, well, what's happening at all of these different energy levels? Each type of atom, rhenium, selenium, and chloride, has its own set of energy levels. And there are sections of those energy levels, and we have names, well, we use letters to represent them, S, P, and D, and then it goes on from there. In this case, we just focus on S, which is closest to the protons or the nuclei, P, which is further away, D is the furthest away. So the main point of this slide is that on the right-hand side, we have the rhenium and we have the selenium. And for both of these graphs, on the left-hand side, where the part that's filled in, again, that's the atom itself or the superatomic cluster itself. These are the contributing energies, and it's much higher compared to chloride, which is on the left side of your screen. For the non-filled in portions, that's the conduction band side. That's where the electrons will get excited, will jump to when it gets excited. The biggest contributor is rhenium. So that tells us, okay, if we send energy to this superatomic crystal and the electrons start getting really excited, they'll jump to the rhenium energy levels, and when it relaxes, quote unquote, and settles back down into the crystal itself and releases energy, that's what's actually happening, most likely. This is still all theoretical with our system. Now that we have a little bit of a better sense of what's happening, how do we apply this to technology? So I mentioned before that the current prominent material or atoms that we use are silicon, right? So we make silicon sheets, which is what you're seeing in this picture here, and we use that to help us with our cell phones, with our monitors, with our computers, etc. And so there are many advantages to using silicon. It's the second most abundant element on our planet. It has that indirect band gap, basically saying that the distance between the sheet of silicon, right, that we're looking at here in this picture, and if we were to send energy to the silicon, the electrons will jump up to the next energy level. It doesn't have to jump very high, which means it's a semiconductor. And that's a good thing. That's exactly what we want. And the cost to actually make this is pretty low. When we make very, very large wafers, which is what, again, you're seeing in this picture here, it's safe to actually handle. And it's thermally stable. That's also really important. That's why you don't want your cell phone, for example, to get super, super hot for too long, but you can get hot for a little bit because it will make sure your cell phone continues to work. Once it goes beyond a certain temperature, that's it, it's done. Now the disadvantages. It's still expensive to produce silicon crystals, right? To then make these sheets. We still have to go into our planet. We still have to mine this material. It also has a short life cycle. For example, we know that if we get our cell phones, it tends to last between 2 to maybe 3, maybe 4 or 5 years, depending on how heavily we use our technology, right? Technology just does not last that long. This is part of the reason why. And that's a problem, because that means we have to dispose of our cell phones, dispose of our monitors and TVs, and all of those extra metals that are a part of that technology, they get redistributed back to our planet, and that's toxic to a lot of the soil that's in our planet. It's also brittle. So while large sheets can hold up really, really well, when you hold a single sheet, it fairly easily breaks apart. And that is what contributes to the fact that it's still not the greatest type of material to use. In comes superatomic crystals. So as I mentioned before, the structure itself allows us to tune for the properties that we need, right? So for example, with this solar panel here, we could potentially use superatomic crystals to then build solar panels, because it has the same distance between the electrons that are already sitting in our crystal and the location where our electrons will jump to when it gets excited by the light from the sun. And because of that same difference between the two systems, silicon and the superatomic crystal, we have the potential to use it in a solar panel. The disadvantage and the reason we might want to do this is because solar panels especially they're not bad, but they're not great at converting the energy from the sun to electrical energy, and we need to get better. So in addition to that, I mentioned before about those sheets of the 2D sheets, right, of the superatomic crystal, and how they're covalently bonded or strongly bonded together. That means we could potentially have a longer life cycle compared to silicon. And so having a material that's more durable, that's better able to convert the energy from, say, the sun into electrical energy, and even produce materials that could help with building quantum computers, that could be a game changer. However, we need, again, more people to actually study these crystals. And so with that, what we talked about today is we talked about what a superatom is, what a superatomic crystal is. We outlined the material science techniques that we actually use to study their structure, meaning what kinds of energy, how much energy, how can we get this energy from these crystals? And then shared the properties that could potentially improve our technologies. And so if anyone is interested in following more of my work, because the work is not done whatsoever, feel free to scan my QR code here. You would just use your cell phone. And if you have a QR code app, you just use the app to scan the QR code. It takes you directly to my website. You can also follow me on LinkedIn. Just put my name and I'm right there. But with that, thank you for listening to me talk about superatomic crystals, how awesome they are, how much work that still needs to be done, and for just deciding to learn more about how we can improve our technology here. Thank you.
Thank you so much, LaToya, for explaining just really greatly and like really carefully like complex quantum physics and given us an insight into the work of scientific software engineers. It was really fantastic. I think at this point, I want to remind people that the opportunity exists to ask LaToya any questions you have using the Q&A feature at the bottom of the page. So please feel free to do so. In the meantime, LaToya, if you don't mind, I had a couple of questions myself I wanted to ask.
Sure, go for it.
And so like one question I had was superatoms very much remind me of like polymers in the sense of, you have like these basic units, and from these basic units you can like construct like a super molecular assembly. And then so I was wondering if you had any insight on maybe what the difference between like, a singular superatom is like would be from, let's say, like a base unit of a polymer, either in form or in like how they give structure to larger assemblies.
Yeah, it's a really good question. So the main difference is that, let's say with a polymer, when you're putting together a polymer, which is essentially what's similar, let me go back. What's similar between a superatom and a polymer, for those who may not be aware, is that it's a bunch of atoms that are bonded together and they have these properties that we can use. An example of a polymer could be plastic, right? There are recipes of polymers, and those recipes of polymers for plastic, they each have their own unique properties. Some recipes mean that the plastic is incredibly durable and therefore very stiff. Others could be that the plastic is very flexible but still won't break, right? That's an example. For a superatom, the difference between the two is the fact that when you put this assembly of atoms together, they don't have new emergent properties like a polymer does. They have properties that atoms already on the periodic table already have. So they're basically copying, quote unquote, the properties of, let's say, a silicon, right? So the system I studied was a 16 atom cluster. There are 8 rheniums, 8 seleniums, 6 rheniums, and 2 chlorides, right? And by putting all of that together, they actually copy the properties of silicon. They don't have new emergent properties because we put all these atoms together. And so really that's the main difference between the two. It's, if we do this, we copy that, therefore we can replace the material we already used with that thing.
Okay, thank you so much. That was a really good explanation.
Yeah.
So we actually have a question in the Q&A feature. and it's from Alan. And Alan first wants to say thank you for the talk. And he later asked, how much longer is the lifetime for the new materials, which I'm assuming are the super atoms, like super assembly versus silicon?
Great question. And the answer is there's more research that needs to be done to study these. So to give a little bit of context, the first paper that I've seen, let me actually not even say paper. The first time that my system in particular was manufactured was in 1980. And it was only manufactured once. And then there was a long stretch of time where nothing else was done because, frankly, it was incredibly difficult to manufacture. There have been improvements in the material science engineering aspect of it, actually making the material in the lab. And so it really hasn't been until the last 10 years or so where research papers started coming out about superatoms. So we still only have a very rudimentary understanding of, for example, what's their life cycle? How can we enhance their magnetic properties? How can we turn this superatom into a superconductor? What is the critical temperature for that? We still don't have answers to those questions yet.
I guess to piggyback off of the question, so I guess now that there are improvements in the material science aspect of it in terms of synthesis, do you think that there's anything unique that computational studies of the superatoms can like elucidate or discover that, let's say, like laboratory experiments can?
Oh, that's a good question. It's yes and no. So the way it kind of works right now is that because it is so difficult to manufacture these in the lab, the material science engineers, they need the evidence from the theorists to say that it's actually worth trying to manufacture this material. And then from there to study the material in terms of confirming the properties that theorists have already theorized, basically, or hypothesized based on using computational techniques. So there's that angle of it. It's less linear than that. So essentially what's happening is that we can discover new properties using computational techniques, but that doesn't, and it could mean that they discover that in the lab. The thing is they then have to develop the methods to then discover that in the lab. That won't break the material down, right? So there's this constant back and forth between the theorists and the engineers to work together to discover what the new emergent properties are. Because theory is great, but it's not helpful if you can't actually physically manifest it or build it in the lab.
Okay.
Yeah.
I guess to piggyback off of that question.
Yeah.
And I'll get to, we have another question in the Q&A. Oh, sorry, we have another question in the chat. Is it that do you also have the capability to, let's say, simulate mechanical properties of the superatom, or right now is it only like electronic, like quantum mechanical properties?
Mechanical as in what way?
Like deformability or...
Yes, we can. So we're not there yet, but meaning that in terms of scientists studying superatomic crystals, we're not there yet. But there is a branch of solid state physics / quantum chemistry, because we all intermingle with one another. These materials are called moire materials. And so this is where you have, let's say, a sheet of graphene. And for anyone who's not aware, a sheet of graphene is basically a sheet that's made exclusively of carbon atoms. and is incredibly strong and flexible and has all sorts of applications, etc. So there are solid state physicists who study moire materials, graphene being one of them. So meaning that if we have a sheet of graphene and we twist it slightly, what new properties emerge from that? If we dope it, meaning we add an extra electron to this sheet of graphene, what are the emergent properties? How does this change the physical structure? Because it does. It changes the physical structure of this graphene, the sheet of graphene. So we have the techniques to do it because the ones who focus on moire materials have already developed them. It's just now applying them to superatomic crystals. And that we have done, yeah. So it's been mostly focused on electronic structure.
So we do have another question. And this one is from Miranda, who asked, do folks make stable superatom compounds, which could, say, be dissolved in a solvent? For example, like a superatom chloride.
Oh, that's a great question. And the answer is yes. So there are superatoms. There's two answers to that. So there's superatoms that can be made by using a solvent, because the solvent helps with the assembly of the atoms to put them together. And then the other answer to that is superatoms can exist as a liquid. They don't have to be a solid object. So yeah, the answer is yes.
Okay, thank you so much for answering that question. I do have and Miranda says thank you so much for answering the question. I do want to solicit people for any other questions they may have. Otherwise, I can ask my last question, and then I will pass it over to Elon to close us out. So this is just a reminder, if you have any questions, you can either use the chat feature or the Q&A feature at the bottom of the page. Okay, so I don't see any new questions. So this is a relatively, I guess, simple question. Can you find superatomic crystals in nature? And if so, what's their prevalence?
Oh, that's a good question. And it is actually simple. The answer for right now is no. From what I've seen so far in the research, all of the superatomic crystals were manufactured in a lab. They were not found so far to exist in nature.
Okay.
Which doesn't mean it can't happen, but we haven't found it yet.
Okay, thank you so much.
Yeah.
And there's one more thing. Miranda wants to give a shout out to Brooklyn College.
Brooklyn.
Brooklyn. And that being said, shout out done, questions done. I'm gonna pass it over to Elon. Take it away, Elon.
All righty, LaToya, thank you so much for such an excellent talk today. I was very interested in this, and me personally, I love to see this kind of work being done. I got my start in material science, so this is very cool stuff. And keep up the good work, because it seems like you're just scratching the surface here. All right, so with that, I'd like to thank everyone, attendees and panelists, for joining us today for another month of our Innovate seminar series. And I hope to see you next month for the next speaker. Carlton, do we have that confirmed yet?
Not at the moment.
Not yet, but be on the lookout for a save the date. Oh, well, actually, we'll probably be resuming in January now that I think about it, because the end of the month is the holidays. So happy holidays, everyone. Get through those finals. Thanks for logging on today, and we'll see you guys in January.